Our next two tests for convergence testing is the integral test and the p-series test. The integral test says that if f is a positive, continuous, and decreasing function when x is bigger than or equal to 1, and the rule for our sequence is equal to f of x, then we can make the conclusion that the infinite series from 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx will both either converge or diverge. So we're going to apply the integral test here, and what we're going to look at would be f of x equals x over x squared plus 1. And before we can use the integral test, we have to make sure that it fits the criteria, that it's positive, continuous, and decreasing. And if you look at this, it is continuous. There are no breaks in this graph. It's positive because we're looking at x values greater than 1. So this f of x is positive for all x. And then what we now have to determine is whether or not it's decreasing. And what that means is that a sub n plus 1 is going to be less than a sub n. And we're going to look at this in a general case. So the n plus 1 term, we'd have x plus 1 over x plus 1 squared plus 1. The big question is that less than x over x squared plus 1? And we can cross multiply here. We get x cubed plus 2x squared plus 2x. And then we get x cubed plus x squared plus x plus 1. And if we get everything to one side, we end up with 0 is less than n squared plus n minus 1. And this would be a quadratic that's opening up. And this is true. I'll switch back to n's. For all x bigger than or equal to 1. If you plug in x equals 1, you're left with 0 is less than positive 1, which is true. And for any other positive value of x bigger than 1, you'll end up with true statements. So, the integral test is applicable to this problem. It is positive, it is continuous, it is decreasing. So what we're going to look at now is the integral from 1 to infinity of x over x squared plus 1 dx. And for this we're going to need a u substitution. And for this infinite integral, we change it so it reads limit as b goes to infinity or some other parameter of 1 to b of 1 over u du. So this is what we have at this point, and now we evaluate the integral, and we have 1/2 limit as b goes to infinity of the natural log of b squared plus 1 minus natural log of 2. Properties of logs allow me to combine it as such, and the natural log is a divergent function as we go to infinity. So this limit is an infinite limit, so this diverges by the integral test. Here's a second example. And if we check this, this is continuous again. It's also positive. Big question is the n plus 1 term. Is that always going to be less than the n term? Again, we can cross multiply. And we can get everything to one side. And this is true for n values bigger than or equal to 1. So integral test applies. Integral test again says take the integral from 1 to infinity of this function. And if this converges to some value, then our infinite series will also converge. And this 1 over x squared plus 1 is just the arctangent. The arctangent of 1 is equal to pi over 4. And then the limit as b goes to infinity of arctangent of b is pi over 2. So this limit converges to pi over 4. So this converges by the integral test. Then there's the p-series test. It's a real simple test. If we have a series to infinity of 1 over n to some exponent, this series will always converge if p is greater than 1, and it will always diverge if p is between 0 and including 1. If p is equal to 1, it has a special name, and it's called the harmonic series. And the harmonic series will always diverge. So the question here, does this converge or diverge? It converges by the p-series test. P is equal to 2 here. we can use the integral test to prove that this is the case. So this is the same thing as we would be using x to the negative 2 So since this integral is equal to 1, since it converges to 1, this series would converge by the integral test. Now, this one isn't directly applicable to one of the tests we did today, but it's similar to the harmonic series, which diverges. And we can draw some conclusions from this. I'm going to jump over to my calculator and do a little bit of numerical exploration here. So I'm in sequence mode, and I set my start value for n to be 2, because that's what it tells me to look at, and then I put in the harmonic rule, 1 over n. Then to the second space, I put 1 over n natural log n. What I can now do is I can generate terms of this sequence and then find the partial sums. So I'll go up to 10. And I'm going to store this into list 1. And then I'm going to do the same thing with V. Evaluate the terms from 2 to 10. I'm going to store that into list 2. And then we looked in class at how to find the partial sums for this. I can go into my list feature over to ops, and choice 6 is the cumulative sum. And I want the cumulative sum for list 1, and I'm going to store that into list 3, because I'm going to look at these terms. And then I'm taking the same thing, I'm going to do the cumulative sum with my list 2. So I'm going to be comparing the partial sums for my harmonic sequence and for the harmonic series and the one that I'm looking at in this problem. So now into my list editor. If you look at these terms, these are the partial sums for the harmonic series. And then the next column are the partial sums for the one in question in this problem. As we go bigger with partial sums, the terms of my series are always smaller than the terms for the harmonic series. So what that means is that this one has to diverge too. Since 1 over n has increasing partial sums, and diverges, and our partial sums has increasing partial sums, that are always less than well, not always, but as n goes to infinity, they're always less than. Our series has to diverge. And we're going to do a lot more work with some comparisons later on in these sections.